Yeah.
What's the plan for tonight?
Plan is to finish concentrations and answer any questions that you guys have.
Review wise.
Mm-hmm.
Should I read?
Yep.
Do you have an extra of the
The study guide? Yeah, right here.
Thank you.
Mm-hmm.
We take tests in class.
Yes. So next class exam is in class. We ready to move on? Okay. First thing we're going to talk about are dilutions. I don't know if there's two L's or not. What?
Right?
Is there two L's?
In dilute, it's just one.
Okay, that's what I thought.
Yeah.
Are we ready? Okay. So let's start simple. What does it mean to dilute something, guys? You guys know this? What does it mean to dilute something?
To decrease the dense.
Decrease the concentration. And how do you dilute a solution?
Pour more water.
Add water, normally, right? Because water is the universal solvent. So we just add solvent to dilute it. But most time it's just water. Okay? So if I have a container here that has a little bit of water and you put some food coloring in it, kind of looks something like this. And then all we do is dilute it by adding water. And it makes it look something like this. You with me? Less red. Okay? So we know molarity is equal to what? Moles over liters. And if I want to change this to an equation, I can say molarity is equal to N over V. Y'all with me? N is the number of moles we've been talking about. Okay? So if I want to solve for the number of moles, I can multiply V to both sides, and I get the number of moles is equal to MV. Are we good? Okay. Now, if I have N number of moles of red food coloring in my first container, we call this N1, and I have N number of moles in my second container. Can you compare those?
Same.
They're the same because I'm just adding water.
Yeah.
I'm not changing how much food coloring I'm putting it in. You with me? So it's the same number of moles. So I can say N1 is equal to N2. Good? Now I have a concentration 1 here, and I have a volume 1. I have a concentration 2 and a volume 2. They're different. You with me? So can we write this equation in terms of concentration and volume? We can. It is, well, number of moles is M times V. So it's M1 times V1 is equal to M2 times V2. You with me? If you want to just memorize the equation, you can ignore all of that other stuff. But this is the equation we use to calculate either our new concentration or the volume of a concentration, right? Any questions so far? Yeah.
If you're adding, um, if you're adding water, wouldn't your volume increase?
Yes. What would happen to your concentration though?
It goes down.
It goes down. So one goes up, the other goes down, keeping it the same.
Okay, so it wouldn't be like, so I guess like you can't say M1 is straight equal to M2.
They're not. But N1 is equal to N2. When we dilute it, when we just add water, the number of moles of solute doesn't change. Does that make sense?
Yeah.
Any other questions on that equation?
Yeah, well, I was like overthinking it when I looked at it. I was like, oh, you're just replacing the volume and the concentration.
So we're changing the volume and concentration.
Right.
And like she said, is if you increase the volume by putting more water, the concentration is going to go down. So the product of the concentration and the volume stays the same during dilution only, right? This is only when we dilute something. Okay, so let's do an example problem, unless you have any questions. Okay, it says, yeah,
So for the ME, VE equals to M2, V2, it means M goes down and V goes up.
or other way around.
So, but in this example you gave me, is the M going down and V goes up?
That's up, that's correct.
And also M equals to mole L, so it means the mole keep the same and L goes up. So it makes M goes down.
Yeah. Yep. Okay, so we need to make 350, in fact, let's start simpler. Let's start simpler than this. Let's say I have 100 milliliters of a 5 molar concentration of sodium chloride, water solution, salt water. Good? And I want to know the new concentration if I add water to make it now 500 milliliters. So what is my new concentration? Everybody understand the question, the problem? Okay. So, which is my first solution? 100 milliliters of a 5 molar solution, right? That's my solution 1. And this down here, what I'm looking for, this is my solution 2. You with me? So what is my M1? Molarity is the concentration. You with me? 5 molar concentration. And my V1 is the 100 milliliters. And my M2, that's what I'm looking for, my new concentration. And my V2, my new volume after dilution, I added water. How much water did I add, guys? 400 milliliters. You with me? So I'm changing the concentration, so now I use by diluting the solution. So I use the formula M1 V1 equals M2 V2. And solve before we plug numbers in?
Sure.
Yeah, okay. So we're gonna solve for M2, that means we do what?
Divide V2.
Divide V2 to both sides. And then we just plug our values in. So M1 is 5 molar. Go ahead and write your units down so that you can use dimensional analysis. Multiply V1, which is 100 milliliters. Now, do I need to change that to liters? Well, let's just find out, right? No big deal. Let's find out. We either do or we don't. But if we don't use dimensional analysis, we don't know.
Well,
If they're the same though on top, wouldn't they? Sorry.
Yeah, we use dimensional analysis so we know. That's why we use it on every single problem. Even this, if this isn't a conversion problem, right? Which it's not. And our V2 is 500 milliliters. What cancels? Milliliters goes away. You with me? Did we have to have liters? No, we didn't. The only way we'd have to convert is if one was measured in liters, one was measured in milliliters, right? Okay. So our answer is going to be measured in moles per liter or molarity. So I get what? A molarity of 1. Does that make sense? Of my sodium chloride solution, right? And I have 500 milliliters of that. Does that make sense, guys? Questions? Should we do more of an applied problem? Okay. So a lot of times we do some reactions with hydrochloric acid, and sometimes we need a high concentration, sometimes we need a low concentration. So when we order it online, do we just buy all the different concentrations we might use? We'd have a lot of bottles in the stock room, right? So what we do instead is we buy a bottle of 12 molar concentration of hydrochloric acid. High concentration, then we just pour a little bit in and we fill the rest up with water. You with me? And we can make whatever concentration we want. So that's what we start with. And let's say I want to do a reaction. I want 350 milliliters of a 1.5 molar concentration of hydrochloric acid. How do I make it? Okay, so do we have two different solutions here? Here's my first solution. And what I'm looking for, this is my second solution. Sound good? Okay. So what's my M1? 12 molar. And I don't know how much of it, I don't know how much of it that I need. You with me? And my M2 is, well, that's what I'm looking for. That's what I'm trying to get, rather, sorry. 1.5 molar. You with me? And I know I need a volume of 350 milliliters. You following me so far? Okay. So it's the same equation. M1 V1 equals M2 V2. And we're solving for V1. So let's divide both sides by M1. Okay? Plug the values in. 1.5 molar. Multiply 350 milliliters. Divide by 12 molar. What cancels? Molarity does, right? And I'm left with milliliters. So I do my math, and I get something like 43 milliliters, is that right? Do the math. 43.75? So I'll just say 44 milliliters of this. Did I make this yet? No. So I get my little beaker and I fill it to the 44 milliliter mark. No such thing as one of those marks, but okay. Maybe fill it in a graduated cylinder, dump it in, right? I don't have it yet. So what do? I just add water. I dilute it. Because this is 12 molar. That's way too high. So I just add water. How much water do I need to add? I just pour water until it reaches at what level? 350 milliliters. Done. So 350 minus 44, what is that? 306 milliliters of water. Good? Question?
Yeah. Okay. So the bottle was 12 molar,
Uh-huh.
and that was, why did we put a 1 there underneath? I know it's
I'm
not
just
much,
saying this is my first concentration, my first solution.
Right, and
And this is what I'm trying to go to. That's my second solution.
the second solution is what we're trying to make.
Yeah, uh-huh.
Okay, alright, okay.
Yep.
Got it.
And so I just label 1 and 2 so I can know what M1 and M2 is, right?
Okay,
Yeah.
understood.
The 44 ml is HCl, and the 350 ml is HCl plus water.
So they're both HCl. They're both HCl. The 44 milliliters of 12 molar concentration of HCl.
She's saying the 350 milliliters is that, the new mixture is.
That's right. The 350 is the 1.5 molar concentration.
Okay.
Did I answer your question okay?
Yeah.
So we just use this.
But both of them are all combined with water,
That's right. Even this one has water in it.
just a different concentration.
Yeah. You put a drop of this in your eye, you're gonna go blind. You put a drop of this in your eye, you're gonna and it's gonna bother you, but okay, you get water in there and you'll be fine. Good? All right, we good? So don't be dumping that stuff in your eyes, guys.
Alright, we can plan through.
Thank God, I was gonna drink it anyways.
Any questions on that? How to use the dilution equation? Is it on your reference sheet? It's not.
Of course not.
So just remember it. M1, V1. The molarity times the volume is always the same. The number of moles doesn't change when you dilute it. So you have to know molarity, moles over liters, times liters to both sides, molarity times the volume, right? And that has to stay the same. So M1 times V1 equals M2 times V2 equals M3 times V3 equals M4 times V4, and so on. Stays the same if we just add water.
Where is this on the worksheets? Which section is this?
The very first section.
Oh, wow.
Did you want to try one on your own? Okay, do it. Try the first one. So make sure you know what the question is. First one is kind of like the one we just barely did. How much water would we add? So you have to, that's a kind of a two-step problem. And the next one is we want to know the volume of a new concentration or of an old concentration. Is there any way we can make a lower concentration higher? We get rid of water. How do we do that?
Evaporate.
You boil it off, right? Can you use this equation for that? Yes, because we're not changing how much solute we have. We're just changing the concentration. Number of moles stays the same.
We're doing number 2, right?
Whatever one you want.
I mean, as in,
So I said just do the first one, but so remember when you're done, go back to the question and ask yourself, did you answer the question it's asking? Because this one is a two-step problem. Don't just put numbers in, plug and chug, and say I'm done.
gone over milling equivalents yet?
No, we're gonna do that next.
Okay. I tried understanding that from the book, but didn't get it.
Yeah, it's a little weird. It's not hard, but it's just
Yeah.
a little different.
It was a conceptual thing where I was like, I don't know what he's trying to tell me. It was like this kind of a small thing in the book.
Yeah.
Do you have the next questions answer? The second one?
Oh, the answer?
Yeah.
Yeah, the answer is, for the second one is 0.6 liters, or 600 milliliters. Good?
Do we need to remember the 1 mole gas equals to 22.4 liter? I mean, the previous, chapter 8. Do we need to remember? And it's-
If you're gonna be doing stuff like that, you do.
we need to remember it.
I would try to remember everything. But if you look at the study guide, that'll tell you what you need to know for this exam.
But you can figure that one out with the ideal gas law. Cause you could memorize that for standard temperature and pressure, but if you plug it into that P times V equals nRT at standard temperature and pressure, that's what comes out.
Oh, we can calculate it.
Yes, yes.
Good, good.
I ran into that as well.
What did you say the answer was to the second one?
The second one was 600 milliliters. Okay, any questions on these guys? I have the answer up here for the first one. So the volume, second volume is about 333 milliliters. But that's not the question. The question was how much water do we add? So we subtract the 100 milliliters that we started with, and we add 233 milliliters of water. We good? Does anybody want to go through that? Yeah? Okay. So it says, how much water would we add to 100 milliliters of a 0.5 molar concentration of sodium hydroxide? And we wanted the final concentration to be, so we want to go from here to a 0.15 molar concentration of NaOH. You follow? So this is my first solution, and this is my second solution. So M1 is equal to 0.5. Good? V1 is 100 milliliters. M2 is 0.15 molar. And V2 we don't know. So we just use that equation. M1 V1 equals M2 V2. And we're going to look for V2 here. Divide M2 to both sides. We good? Put our values in, 0.5 molar times 100 milliliters. Divide 0.15 molar. And we get that our molarity cancels. We do the math, and we get 333.3 repeating milliliters. You follow? Okay. But that's not what it's asking for. It's asking for how much water do we add to the 100 milliliters. Well, this is what we end with. Does that make sense? So we do 333.3 repeating minus 100, and we get 233.3 repeating milliliters of water. Good?
Just wanted to
No, you're good.
solidify there.
Any other questions? Yeah.
Can you do number 2?
Yeah. Says how many milliliters, so we're looking for a volume, right? how many milliliters of a 0.5 molar concentration can be made by adding 25 milliliters of water. No, sorry. That's not what it's saying. By adding water to 25 milliliters of a 12 molar solution of hydrochloric acid. You follow? Okay. So this is my V1 this is my solution 1 or solution 2? Does it matter? It doesn't. It really doesn't matter. Okay? But this is what I start with, right? So that's why I like to call that 1. And what I'm ending with, that's my solution 2, but it really doesn't matter. Okay? So M1V1 equals M2V2. And that means M1 is equal to 12 molar. V1 is equal to 25 milliliters. M2 is equal to 0.5 molar. Are you following me? And V2 is, that's what we're looking for. Right? We're not looking for how much water we add. We're looking for how much of this new concentration we will have if we add water to this. So we're looking for V2, divide both sides by M2. And that's 12 molar multiplied 25 milliliters divided by 0.5 molar. You following me? And molarity cancels, leaving us with milliliters. So do 12 times 25 divided by 0.5. And we should get 600 milliliters. Do we? Okay. Because sometimes I have my answer wrong. So. Anything else? All right. Let's move on to equivalence. So this is a new type of concentration. And we use this, this is a low concentration, but we use this for like, what? How much iron do I have in my blood, for example, right? And wondering how deep I should go on this. So if we have, I'm just going to keep it straightforward. How's that?
Yeah.
Yes.
Okay. So now normally it's measured in moles. How many moles you have per equivalent. But we don't measure things in moles. In real life, we have grams, right? So we're going to do grams per equivalent. And basically what this is, just like molarity is moles per liter, and we can use that as a conversion factor, right? We're gonna use this as a conversion factor more than anything else. Okay? So to find one equivalent, this is equal to the molar mass of our ion, because equivalence is used to determine how much of the ion is in the concentration. Okay? So when you have iron in your blood, is it big chunks of metal in your blood? No. What it is it comes from a salt, maybe iron sulfate or something, or iron phosphate maybe. And it dissociates in your blood, and so it has the iron ion in your blood. We gotta calculate how much iron is in your blood, iron ions. Good? So it is the molar mass of the ion divided by the charge of the ion. And the charge, we're going to put in absolute value. What does that mean? We don't care if it's a positive number or negative number. It's going to be positive, right? So we don't have to worry about negatives here. Okay, so if we have iron 3 plus in our blood, from maybe iron phosphate, for example, let's find out what one equivalent of iron that is. So one equivalent is equal to, what's the molar mass of iron? 55.85 grams per mole. You with me? Per charge. What's the charge of iron 3 plus? 3. Okay. And we do the math and we get 18.61 if I did it right. Grams. So one equivalent of iron is equal to 18.61 grams. But it's grams per mole, guys. But we're never going to figure out how many moles we have in our blood, because this is not something we can measure, right? So it's just a conversion factor, 18.61 gram per equivalent. And that's what it is for iron 3 plus. If we did a different ion, we'd have to figure that out. Molar mass divided by its charge. That means we'll be given its charge, or we'll be given the formula. So if we have sodium chloride, what's the charge of sodium? 1 plus. And we can find out how much sodium we have in our blood, right? Or in our, okay? But then it's just divided by 1, because its charge is 1. Good? Y'all with me? Y'all know how it's 1? Okay. So now let's do a problem off of this. So how many equivalents of iron are in a blood sample containing 0.00120 grams of iron in 50 milliliters of blood. Okay, we already know the grams per equivalent from the last problem, right? And that's if we're dealing with Fe3 plus, and we are. Okay, if we was dealing with Fe1 plus, then it would be different, right? Okay. So what do? This is just a conversion factor. So we are going to just convert, use dimensional analysis. Start with what we know, we have 0.00120 grams of iron. And I don't want grams, so I'm going to use this guy right here. Put grams in the bottom, 18.61 grams of iron per 1 equivalent. I do my math and I get 0.0645. No, sorry. 0.0000645 equivalents. Is that very useful? No, it's too tiny. So instead of equivalents, can we change it to milliequivalents? Did that scare anybody when I said that? What if I had liters and I wanted to change it to milliliters? Can we do that? It's the same thing, right? Just a different unit. So we take 0.0000645 equivalents. Did I get that right, guys? Okay. And I'm going to convert this to milliequivalents. So 1 equivalent is equal to 1,000 milliequivalents. Good? And so I get 0.0645 milliequivalents. Can I also change that to microequivalents? Yeah, same way. Does that make sense?
Would you just write it with 10 to the negative 5?
You could.
Move it?
You definitely could. I just wrote it like this, so, you know, yeah, no big deal. It's the same value.
How do we know the iron is 3 plus charge?
Because it tells us. It didn't tell us in this problem, but I told you it was for iron 3 plus. So on the problem, it will tell you that. Or it'll tell you what the compound is that it came from. So for example, it says, okay, there's iron phosphate. And this is okay, something like that. Can you guys figure the charge of iron? Do you remember how to do that? Oh, no, not again. We're doing okay? Okay.
Yeah, same.
So what's the charge of phosphate?
-3.
3 minus. And how many phosphates do we have? Uh-oh. No parenthesis. We only have 1. This side has to be the same. To cancel out, there's only 1. So this is a 3 plus ion. You with me? I don't think I'll make it that hard for you. It says I don't think, but if we look at the study guide, it'll tell us what we need to know. So hopefully we looked at that study guide. If we haven't, do. Okay? Yeah.
So, on the compound, sorry, would you, if it's asking for the full thing, or is it just gonna ask us for either iron or?
Iron. It'll say iron.
One of the two.
Mhm. Because, yeah. So for equivalence is dealing with the charged particles. Okay? So that means after it's dissociated. Uh-huh. And to calculate it, it's the molar mass divided by the charge. So if we was talking about the whole thing, what's the charge? 0. You can't divide by 0. You with me?
Yeah.
So it is just of 1 ion. Yeah.
So then, what is the semantics of equivalence, like as a unit then? Is it just for ions, and
Uh-huh.
what's the value of that over moles if you?
So 1 mole of Fe3 plus is equal to 3 make sure I got this right. 3.
Would be 1/3.
Is,
Never mind.
grams, no, this is 3 equivalents of iron. Because when we did it over here, then this is grams per mole. The mole's on the denominator, right? So yeah, I had to make sure I had that straight in there. But, and if it was 1 mole of chloride, there would be what? Just 1 equivalent of chloride. But in real life, we don't use moles. So that's why we change it to grams per mole, and then that's why we divide by the charge.
So with that problem we just did,
That's why I didn't talk about this first. Yeah?
with the problem we just did, the 50 milliliters of blood doesn't matter, right?
Yeah, it didn't matter. Because it,
Pick out pieces.
yep. Because because when we started this, let's see, where are we? We had grams of iron and equivalents per gram of iron. It didn't say anything about milliliters. You with me? Or anything about solution for that matter.
So if it would have said like solution, then it would matter.
Yeah. That's why dimensional analysis is so powerful, guys. You don't have to know a whole lot to do this. You just make sure the units cancel appropriately.
So it's just a unit to get us from something to moles, or I guess what's the application?
It's basically, this is what it's, why did they do this? Probably because somebody started it and it stuck.
Torture, maybe.
Probably, no, it's just a way of saying, okay, if you said there's so many grams of iron in your blood, well, I don't know if this is true. I'm just saying what I'm thinking, okay? Its equivalence is just a unit that we're familiar with.
Okay. That makes sense then why I don't.
Yeah.
Got it.
We good? So what do we need to know? How to find the equivalence. So molar mass divided by the charge. Good? And if we look at the study guide, number 17, know how to determine the number of grams of one equivalent. Molar mass divided by the charge is the number of grams per one equivalent. Yep. Any questions on equivalence? And I think this is more used for biological systems, so that's why we're talking about it in here. Okay?
What is the unit for equivalent? Is gram or gram or?
It's equivalence, EQ. One equivalent is equal to so many grams. And it's really so many grams per mole. It really is. But basically, it's a conversion factor. And in real life, that's what we use it as. Okay? Yeah, it's weird. You just learned your Chinese today. Wait. Not really. Just kidding. Any other questions? Okay. The next one is osmolarity. What does that sound like? Molarity and osmosis. What is osmosis? Transferring of particles, right? So you have, so like for, what's it called? I always forget this name. So when someone has bad kidneys, they do dialysis, right? So you have this dialysis tubing that their blood runs through, right? And I don't know exactly how it's done, but I think they put it in a solution, is that right? Have it run through a solution. And depending on where there's more particles, it's going to go one way or the other, right? That's what osmosis does. So particles will go through the osmosis tubing one way or the other, probably getting particles out of the blood. I don't know for sure, because I'm not a doctor, but okay, the particles coming out of the blood into the solution, and then it reduces the concentration that's in your blood of that particle, right? So we're dealing with particles in the solution. Are there particles in our solution? When you throw salt in the water, what happens? It dissociates, right? And now you have multiple particles in there. So if we have sodium chloride, how many different particles do we have? 2 particles. You with me? If we have calcium chloride, how many particles do we have? 3. We have 1 calcium and 2 chloride ions, so that's 3 particles. Does that make sense? Here's a hard one. It's only hard if you're not paying attention. C6H12O6, this is glucose. How many particles do we have? 1. Why is it 1? Because this is a covalent compound, and it does not dissociate. It's not made of ions. You with me? Only ionic compounds will dissociate. So osmolarity is equal to molarity multiply number of dissociated particles. And I'll show you where we use this in just a minute. We good? So you know how to calculate molarity. It's moles per liter, moles of solute over liters of solution. Then we have to multiply by the number of particles. So that means we have to know what the solute is. So we know how to count how many, right? So let's do an example. We have 1.05 moles of magnesium chloride in 3.5 liters of solution. I want to know what the osmolarity is. Sometimes we just call osmol, kind of like molar solution, osmol solution, okay? So osmolarity is just molarity times the number of particles. How many particles do we have in this? 3 particles. So now I just have to find the molarity and then multiply by 3. That's it. So molarity is what goes on top? Moles of solute. So what goes on top? 1.05 moles. And what goes on bottom? 3.5 liters of solution. And then so that's the molarity. Change that to osmolarity times by 3 because there's 3 particles. Good? We do that and we get 0.9 osmol of magnesium chloride. Questions?
Could you scroll up a little bit?
Uh-huh.
Did you write that equation down?
Yes, right there.
Oh,
Yeah.
The dissociated particles means it can dissolve, so we need to remember that table, which is dissolved. And
Yeah, if it doesn't dissolve, then it's just one particle. Yeah.
So you only calculate the.
Well, it's not even one particle. If it doesn't dissolve, then it's irrelevant, right?
But you won't ask us that, right?
Yeah, it's ain't gonna keep it straightforward. But you still need to know the solubility chart, right? Okay.
So in the test, will you test us this, treat us
No, I'm not gonna trick you.
like something indissolved and then ask the particles?
No, Nope, won't do that. But if you wanna know what it's gonna be on the test, look at that study guide. All right. Does that make sense to everybody? Okay, let's practice. Let's just practice counting number of particles. NH4Cl. How many particles is in that compound?
1,
2.
And
Yes, that's a positive, that's a negative, right? One of each, because there's no parentheses. That's 2 particles. You good? What about CaNO3 2? How many now? 3. There's the plus, there's the minus. This is 2 of those and 1 of those. Good? What about this?
that 1.
1 because it's a covalent compound. It doesn't dissociate, just 1. So for covalent, there's just 1. Good? You want to talk about why we use this?
Do we need to know why?
Yeah, this would be to your advantage
Yeah.
because I mean, this is the cool part, right? Are we good with osmolarity? Molarity times the number of particles that's dissociated. Okay? So this is going to bring us to colligative properties. It sounds wonderful, right? There's a few colligative properties. We're going to talk about two of them. One is freezing point. In fact, wonder if you guys should try one from example 3, from section 3, just to make sure you got osmolarity down first. While I take it. Okay, try that.
In section 3, right?
In section 3, one is just count the number of particles.
It's 2, because there's 2. I hope so, right?
Any questions? Like, did you get it right or not?
What's the answer?
Let's do them.
Okay, so, did you do the first one?
The first
Yes.
one.
2.43 osmol?
Yes.
Yes.
Want to do it? Okay. All right, so it says 270 grams of NaCl in 3.8 liters of solution. And we gotta calculate molarity, osmolarity, right? So osmolarity is just molarity. Molarity is moles per liter. Do we have moles? No, so we got to convert the grams into moles. 270 grams of sodium chloride. And the molar mass of sodium chloride is 58.44 grams of NaCl to 1 mole of NaCl. So grams goes away, leaving us with moles. And what do we get? 4.62 moles. You with me? Okay, now I know my moles. I'm going to divide that by my liters, 3.8 liters of solution. And this gives me my molarity. Is it 1.22? Or maybe you guys just multiplied by the number of particles. How many particles do we have? 2, right? So multiply that by 2 and you get 2.44 or 43 or whatever. And that's osmol. Does that make sense? Any other questions before we move on? Okay, colligative properties. Every winter we deal with this. We have ice on the road, so we put salt. Why do we put salt on it? Because. Because what does it do? It lowers the freezing point. Therefore, so if it's 0 degrees outside, well, water freezes at 0 degrees, right? And if we lower the freezing point, then it turns back to liquid. Doesn't make it hotter, guys. It doesn't.
I actually didn't know that.
No, that's why we're talking about it. We good? So we have freezing point depression, meaning we're lowering the freezing point. And when we cook, we use this. Did you know by putting salt in your water when you make soup or something, it raises the boiling point? Makes it cook hotter? Oh, yes, I can get it cooking faster. All I have to do is just dump more salt in it, right? Just dump loads of salt in the next time you're making some soup. Wait, not really. Okay, but yeah, it does raise it a little bit. So boiling point elevation. Okay. There's also vapor pressure depression. So you can, so vapor pressure, so your gas comes out of your liquid, right? You can decrease that pressure. And there's also increase of osmotic pressure. But we're going to talk about these two. Is that okay? We're going to keep it simple. All right, so let's do, in fact, if we're talking about particles in there, when you dissolve particles, they dissociate, right? So when we make, when we put, in fact, you guys ever make homemade ice cream the old-fashioned way? With ice and salt? Okay. So we do that with just rock salt, yeah? And rock salt is just sodium chloride. So we have two particles, right? How can we make this freeze faster? More particles in it. So we use ice melt, which is calcium chloride. That has 3 particles in it. That's why we don't use sodium chloride. We don't use table or rock salt for, it looks like rock salt, but it's a different color or has something else, right? It's different, okay? We good? All right, actually, never mind. We'll just keep it simple. So if you have more particles, it changes this. And here's how I remember this, guys. So is it freezing point, depression, or elevation? Well, one of them goes down, one of them goes up. Which one is it, right? So water is between 0 degrees Celsius and 100 degrees Celsius at sea level, right? And what the colligative properties do, if you add particles, it broadens this range, makes it bigger. It lowers the freezing point and it raises the boiling point. Good? All right, so the boiling point of water, so let's do an example. Boiling point of water increases by 0.51 degrees Celsius for each mole per liter of solution. Each mole per liter, what is that? Molarity. But we are dealing with more particles in the solution, so we don't need molarity, we need osmolarity. You with me? So basically this is saying it increases by 0.51 degrees Celsius per osmolarity. Okay?
And it doesn't matter what the solute is?
It does, because if you have
Right.
the number of particles. So if you just throw sugar on the salt, sugar on the ice, then is that gonna lower the freezing point? A little bit, but not as much as salt, right? Because sugar's only one particle, and it's big, a lot bigger. Takes more to dissolve it, right? Okay. So that's not the problem. Here's the problem. Find the new boiling point if we have 8.56 grams of lithium chloride in 75 milliliters of solution. Okay. So what can we find with this information? Concentration in molarity or osmolarity?
Molarity first.
Yeah, we can find molarity. So we got to change grams into moles and milliliters into liters. Yeah. Can we do it as one problem Or would you rather break it up in one step at a time?
Break it up.
Break it up? Okay. So 8.56 grams of lithium chloride. And we're going to convert this into moles. So you have to find the molar mass of lithium chloride, which is 41.94 grams of lithium chloride for 1 mole of lithium chloride. Grams goes away, we have moles. And I didn't calculate this, so somebody calculate this. I did it as just one problem, because it takes up less room, but no big deal. What's 8.56 divided 41.94? What is it? 22? Okay, thank you. 0.204 moles of lithium chloride. And now I need to convert 75 milliliters into liters. What goes on bottom? 1,000 milliliters is the same as 1 liter. Hope we're good at that by now. 0.075 liters. And then we just divide these two to get the molarity, right? So what's 0.204 divided 0.075?
Two point seven two
2.72?
2.721.
And that's molarity. But we need to calculate the osmolarity, so what are we going to multiply by?
2 parts.
Lithium chloride has 2 particles. And that's going to be 5.44, if I did it right. Is that my answer? Oh, we got to go back to the question. What are we looking for? Find the new boiling point. And I increase my boiling point by 0.51 degrees Celsius per osmolarity. So I have 5.44 osmol. Do I want osmol in my answer? No. 0.51 degrees Celsius per osmolarity. You with me? So osmol goes away, and I get an increase of 2.78 degrees Celsius. Is this my answer?
You want it in Kelvin?
No. No? Only in those certain formulas, right? What is the original boiling point? 100.
Plus 2.7.
100 plus, so it increases by 2.78 degrees. So that means my new boiling point is 102.78 degrees Celsius. I know it's not 100 degrees here in Utah, but we just deal with sea level. We good?
What is it? What's
How was our hand?
So where did you get that from?
Where did I get 100 from? That's the boiling point of water at sea level. Should you know that?
Oh, that's like a basic thing.
Yes.
I didn't know.
But as you go up in the mountains, like up in here in Utah, or higher up in the higher elevation, it boils at like 98 degrees Celsius. If we go higher up in the mountains, it's less and less and less. Do you understand why?
No.
because there's less pressure.
Less pressure.
Yeah, so if we look at a pot of water that we're putting on to boil,
And that's like cooking here.
well, once you get a certain temperature, then that water has enough pressure in there to push above and break the pressure that's pushing down. So we got atmospheric pressure pushing down, right? As soon as we get to 100 degrees Celsius at sea level, then it bubbles over and it pushes up and goes against that pressure. But if we go up in the mountains, now we're up here, we have less air pressure. You with me? Less air pressure means less force right here. So we might have just a little bit now, right? And so it'll boil at a lower temperature.
So when we go higher, it's less pressure.
Uh-huh. Does that make sense? And this is why when you go up in the canyon, your ears start, or actually when you come down, then they start popping, right? Yeah. We good? Yeah.
I have a question about the last steps. Could you move on?
Uh-huh.
The 5.44 osmol times osmol 0.15. So if it asks boiling point, how about the freezing point? Is the same equation or in YouTube?
So they'll give you a different value. That'll be given to you. Okay? So if it'll say it decreases by this many degrees per osmolarity. But they'll give you that.
But it's the same equation, right?
We're not using an equation, we're using dimensional analysis. Yes. Same. Good? Now, ladies and gentlemen, we did that in 1, 2, 3, 4, 5 steps. Should I show you a different way?
Sure.
Okay. Here we go. Concentration is amount of solute, what was it? 8.56 grams of lithium chloride per, is it 75 milliliters? Yeah. 75 milliliters. And let's use dimensional analysis here. We're going to do the same values, guys. We're doing the same math. 41.94 grams of lithium chloride to 1 mole. That goes away. 1,000 milliliters to 1 liter. That goes away. Now we have moles per liter. That's molarity. But we want osmolarity. And osmolarity is times by 2 particles, because we have lithium chloride is just 2 particles. And that's osmolarity. And we increase our temperature 0.51 degrees Celsius per osmolarity. So moles per liter times particles is osmolarity. It's still one, well, that's not really a step, kind of. 1, 2, 3, 4, 5 steps. It's the same math, all condensed into one little itty-bitty problem. Which way should you do it? The way that clicks with your brain. Okay? If you don't like this part because it doesn't look like it cancels the osmolarity, then break it up right there. Find osmolarity, and then, right? Any questions? Okay, that's it. Now, on the worksheet, so you have section 5 that has some more problems like we just did. And then section 6 takes it all and puts it all in one problem. Should we do one?
Yes.
Do you care which one we do? First one? Okay. So it says what volume, in fact, I'm going to write the equation first. Uh-oh. HNO3 plus potassium hydroxide gives us H2O plus potassium nitrate. What kind of reaction is this, guys? Acid base. Okay? So it says what volume, so we're looking for volume, right? We're looking for volume of HNO3 solution. Well, that has a concentration of 16 molar concentration. Y'all with me? What volume would you use to react with 5.5 grams of potassium hydroxide, according to this equation? So what do we do first? Balance the equation. So is it balanced? Let's count.
Yeah.
One nitrate, one nitrate. One potassium, one potassium. Two hydrogens, two hydrogens. Four oxygens, four oxygens. Looks like we're good. Well, I already counted that oxygen, so 1 and 1. Good? So it is balanced. Now what? Start with what you know. I know a little bit of this substance, not everything of that substance, but I know something of this substance. So I'm going to start with 5.5 grams of potassium hydroxide because I want to know this substance. So let's convert this into this. Yeah. So convert grams of, should we use the mole roadmap to guide us? Okay, here we go. Somewhere. Might be easier just to take a picture. Oh. Okay, here we are. Here's my grams of my first substance. That's where I'm starting. You with me? Then I use molar mass to convert to moles of that same substance. Hold on, where am I even trying to get to? Liters of my second solution. Oh, here it is. somewhere like right there. Hold on. You guys weren't given that, were you? That's not on your roadmap. Okay, so we'll just, okay. What? Can we make our own roadmap? Should I show you a detailed one? Let me take this picture again. I tried to get you this on the test, but they won't let. We're gonna use this more next semester, or sorry, next unit. Yeah, you guys are with me next semester, right? No!
I wanna miss you. I wanna use that.
All right.
That's great.
So here we go. This will be for next unit, this semester.
Just give us one note card for the final, and I promise we won't tell anybody. I promise we will not tell anybody.
We'll just have it in class.
I will take it to the grave.
I'll think about that.
Hey, it's better than no.
All right. So we're starting with grams of substance A, molar mass to moles of substance A. And we got to go to a new substance anyway, right? So we got to do moles to mole to get to moles of substance B. And then we use molarity. So this says multiply or divide volume, but hold on a sec. What if we have molarity instead? If we have moles, molarity is just a conversion factor from moles to liters, right? So we just use molarity to convert it to liters. Good? So it kind of doesn't say it on here, but let's get to moles anyway. So the molar mass of KOH is something. 56.1 grams. Anybody else get that? Okay, good. To 1 mole. And now we use the mole-to-mole ratio. Well, it's a balanced equation. They're all ones. Woohoo! 1-to-1 ratio. 1 mole of KOH. And we're going to HNO3. Y'all with me? Am I going way too fast? Okay. So things are canceling here. We have moles, and now we have molarity. Remember, this is 16 moles per 1 liter. That's what molarity means. We want moles to go away, so 16 moles on the bottom to 1 liter. And that gives me my volume that I'm looking for. So 5.5 divide 56.1 divide 16. And we get 0.00613 liters, or we can convert that to milliliters and get 613 milliliters. Does that make sense to everybody? So,
Did you say 6.13 milliliters?
yeah, 6.13. You're right. I'm tired. But you guys aren't, so we're gonna be here for another hour, right? We should probably start talking about questions. We're almost out of time. Any questions on the material today? So this was just a little bit of stoichiometry with what we just, kind of all the units that we learned, right? Okay, questions? Yeah,
I don't have like a.
a problem?
It's just, yeah, no problem, just a general question.
Mhm.
I wanna go over the parts per million and per billion.
Okay. Yeah, good. I'm glad you're going over you're asking this. So, percent, parts per million, parts per billion. These are all the same thing, guys. All of them are the same thing. Now watch. Everybody watch this. How do you calculate percent? Parts of solute over parts of solution times what? 100. Because percent is parts per 100. That's what percent means, per 100. How do you do parts per billion? Same thing, times 10 to the 6, parts per million. Parts per billion, same thing, times 10 to the 9, times billion. So if you know percentages, parts per million, parts per billion, same thing. We're just timesing by a million and a billion. Percent is parts per 100.
I never put it together before, cent, 100,
Yeah.
yeah.
Do you get that?
Our solution by,
Parts of solute divided by parts of solution. That's what concentration is always. Solute over solution. Now the parts, they have to cancel though. So you either do grams over grams, kilograms over kilograms, liters over liters, or you can do grams to mass to volume, right? As long as it's a water solution, it has to be grams over milliliters. And you can do that on all three of these. Did I help you?
Do a problem.
Yes. Okay. So if we have 3 micrograms of chloride in 4 kilograms of tap water, I want to know my concentration. Now, I just pulled this out of my head, so I don't know if it's parts per million or parts per billion. Let's find out. So this is my solute. This is my solution. Do you get that? So 3 micrograms of chloride over 4 kilograms of solution. So this is mass and this is mass. So they have to be the same unit. Let's convert everything to grams. Is that okay? So 1 million micrograms is the same as 1 gram. And 1 kilogram is the same as 1,000 grams. And all of our units should cancel. So what are we going to multiply? Is it going to be parts per million or parts per billion? What do we have on bottom? 1 million. Sorry, 1 billion. We have 9 zeros on the bottom. So it's going to be times 10 to the 9 power. Those go away. Woo-hoo. It doesn't always work that way. But on the test, if I ask you, I'm going to tell you what you're going to look for. Okay? So 3 divided by 4 is 0.75 parts per billion. What if it was finding percent? Then what would you do? The exact same thing times 100%. That's it. but it's just a really small percent, right? And if it's parts per million, you just times by a million. Did that help or no?
Kinda, yeah.
How many cents in a dollar?
Anything else? Yeah.
Yeah. So on the study guide, number 11 is determining if given molecules will form a solution or not in terms of polarity. So this includes like miscibility, I assume?
Like dissolves like.
Yeah.
If it's on our solubility chart, well, that's if it's an ionic compound. But this is talking about polarity. So we have to determine if a molecule is polar or not. If it's polar, then it's going to dissolve in other polar substances. If it's nonpolar, it's going to dissolve in other nonpolar substances.
Okay. But for miscibility, do they have to be liquids?
No, I'm not gonna.
Okay.
We're gonna
So
keep.
this isn't going that deep?
No,
I see.
real straightforward. Anything else? Yeah,
Can we do an example of Le Chatelier? Is it going to be like?
yeah,
Okay.
yeah. So like on number 13.
Yeah.
Okay, so if we have H2 as a gas
Yeah.
plus O2 as a gas, giving us in equilibrium H2O as a gas. So if we balance this, it's going to be 2 and 2 right here, right? And let's make it a little more. This happens, this is going to be plus 6 kilojoules of energy, of heat. Okay? So how do we get the reaction to go in the forward direction? This is the forward direction. How do we get it to go in the forward direction?
Pressure.
If we increase the pressure, because most of our gases is on the left, right? If we increase the pressure, those guys are going to collide more often and make more water. So that's going to push it this way if we increase the pressure. What else?
Reduce heat.
What?
Heat. Reduce heat.
Reduce the heat. The heat's on this side, so if we add heat, it's going to push it that way. You with me? So if we reduce the heat, make it colder, it's going to push it that way. What else? Add more of this or more of this. Add more reactants, it's going to react more and push it over. Y'all with me? What happens if we add a catalyst? No effect. That one doesn't change it, right?
But is it going to go into like solubility with different temperature
Maybe.
and pressure? Can we go over one of those?
Solubility, different temperatures and pressures.
Yeah.
So, say exactly what you're wondering.
Because I think solubility goes up with temperature, but is that just for gases into liquids?
No, that's. Let's see. No, you want to. If you increase the temperature, then it wouldn't. It'd make it less. The gas is less soluble because it makes it more disorderly, right?
Right.
So it's going to rather be in a gas form rather than jump into the liquid.
Right. The pressure would.
But you increase the pressure, yeah, and it pushes the gas inside. Because it would, yeah. Good? Anything else? Did you look at these questions? Okay. Look at them before you take the exam, guys. Have ChatGPT help you build some problems from it.
Can I take this tomorrow?
I don't know. It takes up to 24 hours for them to get it in their system.
Okay,
Um,
so maybe.
I can definitely try.
So would I be able to just go and like schedule it if it's available, or is it something that you have to make?
Something I have to make available.
Okay, cool. Should I send you an email to remind you?
Yes, please do.
Cool, thank you.
Okay.
I'm curious about the mole fraction equation. So if this one is correct, can it be the n to v is equal?
So what are you asking?
So if this one is correct, it says in the text,
Uh-huh.
can this one correct as well?
So fun.
I'm just curious.
No.
No?
Nope.
But the v and okay.
They're related, but so, let's see. So n is,
Right.
well, yes. So n is proportional to volume.
Yeah.
So that means
Very good.
it would probably flip-flop, but no, I wouldn't do that, no.
Mm.
But I got it on my boss's desk by Monday.
Just
so-
only use this one.
Yes. So, yeah.
But do you know why? Why it can be equal?
Why it can't?
Yeah.
Because, so, let's see, number of moles,
Because number of mole increase, the value increase as well.
mhm,
Yep. Well, that roughly.
increase.
I do have to technically do that,
but I don't really have
have
to
have those done until April.
Number of moles,
Are you waiting?
maybe,
Maybe. Right?
but we won't have you do something like that.
Okay. Okay. I'm just, yeah. Because these two are related.
Yeah, mhm, yeah,
Because if you say the number of mole
mhm,
increase, then it's
Pressure
related to the
increases,
pressure,
yeah.
So I
Okay.
think that, so it's maybe, right? We didn't do
yeah,
that experiment.
that's right.
Okay.
Will this class be uploaded before Thursday, so I can watch the beginning?
Yeah, I'll try to,
Okay, thank you. I like watching.
can you email me too?
Yes, I will email you.
Because that helps me to remember.
Okay, thank
Because
you.
sometimes when I get home, I just want to go right to bed.
Some
But,
of them were not uploaded, but ahead of our time.
yeah, sorry, it took a while to get everything up.
Okay, thank you.
But hold on,
Yes.
if you go to the website, so the homepage, you can watch last semester. They are up too. They're already there. But definitely, I'll still do this.
Okay.
But if push comes to shove and you gotta learn it, then
Yeah.
okay.
Okay, thank you.
Okay, thanks.